Hello and welcome to Mathematics with Simon. I'm Simon. Today we're going to look at composite and inverse functions as part of the A-level mathematics syllabus. So what is a function? A function takes a number in its domain and turns it into another number which is in its range. So example functions include f of x equals x squared, multiplies a number by itself, g of x equals sine x, h of x equals the reciprocal of x, I of x just equals x, j of x equals x squared plus 4x plus 1. Any quadratic, any cubic, any quartic, any polynomial can be the basis of a function. K of x equals e to the x, and L of x equals 6. Whatever you put in, the answer is 6. It's like a cafe. Whatever you want, the answer is egg and chips. They've got one thing on the menu, it's 6. Every function has a range and domain. So with x squared, the domain is all real numbers, and the range is all real numbers greater than or equal to 0. For sine x, the domain is all real numbers, and the range is everything between minus 1 and 1. 1 over x is all reals except for 0. There's no 1 over 0, so the range is also everything except 0, all reals except 0. All real numbers can go into x, and all real numbers come out. The same number always comes out. For x squared plus 4x plus 1, all real numbers are the domain, and the range is all numbers greater than or equal to minus 3. Someone clever can say in the comments why that is, but a little bit of differentiation would help, or curve sketching would help. We've got a video on curve sketching if you're interested. For e to the x, all real numbers go in, and the range is all positive reals, so e to the 100 is a massive positive number, and e to the minus 100 is 1 over e to the 100. It's a tiny number, but it's still positive. And if the function is just 6, the domain is all real numbers, and the range is a singleton set 6. Now let's look at composing functions. So if we do f(h) of x is f applied to h of x. So h of x is 1 over x, and f applied to h of x is 1 over x squared. H of g of x, so we start with g of x, which is sine, and then h is 1 over, so it's 1 over sine x. But g of h of x is the other way around. That is sine applied to 1 over x. Sine 1 over x. And then we've got h of L of x. Well, L is just 6. So h of L of x is always 1 over 6. And that's different to L of h of x. The order matters here. L of h of x is just 6, because L applied to anything is 6. So L of g of x is 6. Then finally, g of I of x is I of g of x is just sine x, is just g. So combining with I of x doesn't make any difference. And I of x has a very special status, so when composed with any function it leaves it the same. It's like multiplying by 1 or adding 0. So if we multiply 8 by 1 we get 8, multiply a million by 1 we get a million, and then if we add 0 to any number we just get the same number back. And composing with I of x is the same, it's an identity. It doesn't change the thing. Inverse functions reverse the action of a function. So if you've got f of x equals x plus 2, then its inverse, f to the minus 1 of x, is x minus 2. So if you apply f of x to 7, you get 9. 7 plus 2 is 9, and then f to the minus 1 on 9 is just 7 again. Positive square root of x is the inverse of x squared on the set of all positive real numbers. In fact, that's the definition of square root, is it's the opposite of x squared. So if x was 5, x squared is 25, and the square root is 5 again, you go back. 1 over x is self-inverse. So if you apply 1 over x to 7, you get 1/7, and if you apply 1 over x again, you get 7. Log to the base e of x is the inverse of e to the x. Again, that's the definition of log. And to have an inverse, a function needs to be 1 to 1. Otherwise, I mean, the problem is, say you try to look for an inverse for y equals x squared on all of the reals. The issue is this, is that 4 squared is 16, and minus 4 squared is 16. So where is the inverse going to send 16? Is it going to send it to 4 or minus 4? It doesn't really work. So to be able to create an inverse, it needs to be 1 to 1. If you're mapping multiple numbers onto something, you don't know what to map back to. And you can put it this way, in terms of functional composition, f of f to the minus 1 equals f to the minus 1 of f of x equals I of x. So they combine to make the identity. It's a bit like when you say 7 times 1 over 7 equals 1, or 6 minus 6 equals 0. It's the same sort of idea. So in terms of multiplication, 1 over 7 is the inverse of 7. Okay, why does any of this matter? So in differentiation we have the chain rule, which says if we've got the derivative of fg of x, that's just f dashed of g of x times g dashed of x. So it's the derivative of f at g of x times by the derivative of g of x. So for example, the derivative of sine x squared is the derivative of sine, which is cos, at x squared, times by the derivative of x squared, which is 2x. It's really clever. The set of one-to-one onto functions forms a group. In fact, it can be shown that every group is a subgroup of a group of functions. So groups of functions are particularly important, of one-to-one onto functions are particularly important. They're sometimes called permutations, particularly with finite sets. So it's fundamental to group theory, which is part of the further maths syllabus. Now, a lot of mathematicians, probably most mathematicians, think that set theory is the foundation of mathematics, so all mathematics boils down to sets. But there is an alternative which is called category theory, and that would say all mathematics boils down to functions, and the composition of functions of the identity are actually fundamental to the definition of a category. So, in some sense, this can be about the definition of all mathematics, so it's the most important thing. This is kind of a postgraduate idea. I mean, some of these ideas. So differentiation is on the A-level syllabus. You might have done it already. Group theory, further mathematics, and then sort of foundations of mathematics, and particularly category theory, are more postgrad topics. So you don't have to know that if you're doing your A-level, but you might be interested. I hope you like this video. You're very welcome to subscribe and hit the notification bell. I'd love to hear your ideas, and I hope you enjoy your mathematics.